Okay, hello everybody. In this module or module 2 lecture 3, we will talk about transfer function modeling and what we also call as the block diagram representation, and I will shortly tell you what these things mean and the advantages of the transfer function modeling and how the block diagram representation simplifies for us the analysis of systems. Okay, so let us start with an example again. This we have seen earlier. Let us say I start with an RLC circuit, and given a certain initial voltage, I would ask you to compute what could be. So, this is the input. I will ask you to compute what is the output voltage to the capacitor, or even what is I of t, right. So, what would I do? I would start writing down the appropriate voltage loss, that V I is R times I plus L d I by dt plus the voltage across the capacitor, which is 1 over C integral I dt, right. This is the voltage. Now, the problem is find V o for a given V I. Okay. So, what does this mean? That to find that the time response or how V o changes with a given V I, we need to solve certain set of differential equations, ordinary differential equations, or even sometimes integral differential equations. You see the little integral term over here. Okay. So, what we also earlier saw is that when I transform my differential equations into the Laplacian domain or the S domain, the differential equations turn out to be simple algebraic equations, which are then easier to solve. Linear equations are usually easier to solve than differential equations, right. So, we transform the model into the S domain, and then we would define what is called a transfer function, right. And this is a signal which will relate a given input to output, which will be computed again by what is called the transfer function of the system. And this is of course model which is applicable for all kinds of input signals. Okay. So, what is the transfer function of a system? Well, the transfer function of an LTI or a linear time invariant system. Time invariant, again let us recall the definition, that the parameters of the system would not change with time. For example, the mass or a spring constant or a resistance and inductance, all these will be invariant of time. So, for a linear time invariant system, let me also recollect that what we will here focus on systems which are just single input, single output systems, also called seesaw systems. So, for this kind of LTI seesaw systems, the transfer function is the ratio of the Laplace transform of the output to the Laplace transform of the input, assuming 0 initial conditions, right. So, mathematically, if U s is the Laplace transform of the input signal or the input function, Y s is the Laplace transform of the output, then the transfer function G of s is Y of s divided by U of s. Okay. So, how does this again look like? So, I have input U of t and an output Y of t, right, and this is some system sitting here. I can even say some say ordinary differential equation, right, this system is represented by. So, I transfer it into the Laplacian domain, I have a Y of s, and the linear relation which describes how a certain input results in a certain output is called the transfer function. So, given this transfer function, I can simply say that given input signal U of s, the response of the system or the output is simply the multiplication of G of s and U of s. Recall that in the time domain, we would actually have to do a convolution here. Convolution. So, let us say if Y of t is my output signal, let me call G of t as the system and some convolution with the input. Okay. So, now we get rid of these things, right. So, this G of t is replaced by G of s, and this G of s is called the transfer function, right. Okay. So, simpler way or one of the ways of looking at transfer function is to look at the impulse response of a system, right, which means the response of the system when the input is an impulse, right. So, earlier, so what we had y of s was g of s times u of s, right, and then if u of s is an impulse, right, we know that the Laplace transform of an impulse is just 1. So, I am just left with g of s. Okay. So, let us keep it here for the moment. Okay. So, what is an impulse? By definition is it is an infinitesimally narrow and an infinitely tall signal. We can in speaking terms just says that it takes value of 0 everywhere, here it is 0, here it is 0, and except at t equal to 0, it is like an infinitely long signal such that the area is 1. Okay, so how do we construct this impulse signal, right? It might sound a little superficial here, but let us say I start with a little rectangle here, okay, and this rectangle has a width of a and a height 1 over a, right. So, now what is the area of this guy is 1, right, area is a times 1 over a is 1, and if I call this signal as say the rectangle r of t, then I have minus infinity to infinity r of t would be 1, right. There is 0 everywhere else to the left of this point and even the right of this point, and this width is a, right, from here till here. So, you can call this as a by 2 in the negative side and a by 2 in the positive side. Okay. So, based on this, how do I construct an impulse? So, let me take the limit of the signal as a goes to 0, right, nothing changes, right, it is still the area is still a over 1 by a, and the limit of the signal a, if I take the area of the signal, it would still be 1, right, and therefore, I have this signal like this, right, that minus infinity to infinity delta of t is 1. Okay. So, if the input to the system is the unit impulse, then the output is called the impulse response, and you see in that case the output which I observe is equal to the transfer function, at least mathematically I can see that, right. So, that means that transfer function is this transfer function is just the impulse response for an LTI system. Again you look at the initial conditions to be 0. Okay. So, let us do a little example of this. So, I again take the case of simple pendulum, right, a point mass, say everything is normalized to 1, and say if I just measure theta this way, and I say I just give a impulse here, right. Okay, it may not be practically possible to give an impulse like this, but it might, you can just look at it as a signal like this with a very small a. So, what would you expect? I just loosely speaking I just push it away, so that I give it a little push, so it will just somehow follow its natural response, right. If it is a system which has no damping, it will keep on oscillating all the time. If it is a system which has damping, the oscillations will die down. This is a natural response to the system, right. So, or even look at it in a different way, right, say natural response of a human being, right, especially at 7 in the morning, right. So, the alarm clock is the impulse response, right. So, the alarm perturbs you, you just switch it off, everything happens in a flash time, and then you go back to sleep, right. That is your natural transfer function, right, is the sleeping condition, and that is the impulse response. So, but if there is somebody trying to wake you up for a very long time, then your response might be different. We will see how those response will be, but the impulse is just the natural response of the system here. Okay. Now, the question is given a system, how do I find the transfer function? Well, the first step is to write down the equations. So, where do the equations come from? This again come from my voltage laws, KVL, KCL, and maybe even the Newton's laws, right, all those things which we have been dealing till now. So, first write down the model equations of the system. Second, identify the system input and output variables, and we will see that the output, the choice of output can be different, or it is not always unique. Now take the Laplace transform of the model equations, which are essentially differential equations, and assume 0 initial conditions. And then find the ratio of the Laplace transform of the output to the Laplace transform of the input. I can always do this because it is a linear equation, right. Okay. So, again let us come back to this example which we started with, right. So, I have V I as the input, R, L and C the circuit elements generate a certain current I of t, and I want to find what is V naught by V I. Okay. So, this is easy to find out. V I is R I plus L d I by d t plus 1 over C integral I d t, and this is my V naught, right, this guy here. Okay. Now, what is the first thing is to identify the input and output variables. Input is the voltage which I apply, and output I identify as the voltage across the capacitor. Okay. So, my equation, which was an integral differential equation, if I just take the Laplace transform and use the appropriate properties, that a differentiation becomes, like loosely speaking, a multiplication with S, integration becomes a division by S, and I end up with an equation like this. Okay. So, now step 2, identify input, identify output, do the Laplace transform, and the last step would be just take this ratio of V O by V I. So, I can always do this, right, V O by V I, just take this guy divided by V I, I have this one 1 over S C I of S plus R plus S L plus 1 over C S, and I just end up with this transfer function. Okay. Now, I could also do it, you may ask a question, what if, can I just write down here, what if I of S or even say I of t is the output. Okay. This is another choice of output, right. I am say instead of measuring the voltage here as the output, I just measure what is the current. I could always do that. Okay. So, how does the Laplace transform now look like? It's again kind of straightforward to compute from here. So, I say V of S is R plus S times L plus 1 over S C I of S. Okay. Now, the transfer function G of S, okay, just to distinguish between this, put a I here, there is an output here, or I am actually measuring the current as the output, is the ratio of the output I of S over V of S, which from this expression can be simply computed to be something like this 1 over R plus S L plus 1 over S C. Okay. Again, these are transfer functions for the same system, but here I am measuring V O as the output, and here I am measuring the current as the output. Okay. Now, if I just start with some relation between input. So, usually we will throughout this course denote U of t as the input signal and Y of t as the output signal. Okay. So, if I am given a differential equation in Y and U like this with again 0 initial conditions, how do I find the transfer function? Well, again I just do the same steps. I take the Laplace transform of the left hand side. So, Y of S, so I am just differentiating it 3 times, so it will be an S cube, differentiating twice will give me an S square, differentiating once will give me a S, and so on. On the right hand side, I have du by dt plus u, which will just transform to 10s plus 1. So, once I have this, I can easily write down what is y of s over u of s. Okay. So, given this transfer function, what are its properties? Well, the first says that the transfer function of a system is independent of the magnitude and the nature of the input, which means it is essentially system level property, right. It is just based on what is the system at hand, not what is the input signal. For example, if I take a system, just say any system with a transfer function g of s, and I measure certain output with a certain input u of s. Okay. So, if this u of s is an say impulse, I will have a certain output, could be whatever, right. the g of s would be the same as when this could be a step input with a corresponding output, right. It does not really depend on the choice of the input, it is just a property of the system by itself, right. The nature of the pendulum would not change if the input is a ramp or the input is a impulse or even a step, right. The transfer function with the one which transfers in a way a given input signal to an output signal is a property of the system itself. Okay. So, once I have g of s, I can easily study what could be the transfer function for different kinds of inputs, right. For example, y of s is g of s times u of s. So, this is fixed. So, give me any signal u of s, I can always study what is the response, right. If I were to do the time domain, I will just go find the inverse Laplace transform, for which I know lots of tricks by now. And so, once I have the transfer function, I can study the response for various kinds of inputs to see how my system would behave. Well, now is the transfer function unique? So, give me a transfer function, can I say what kind of a system it is? Can I say is it a car, is it a bus, is it an aircraft or whatever? Well, the answer is no, right. The transfer function does not provide any information concerning the physical structure of the system, which means that two different physical systems can have the same transfer function. Okay. So, let me just take example of the mass spring damper system, which we had studied in our earlier lectures. It had a transfer function which was like 1 over ms square plus bs plus k. If I just take a simple case of m equal to b equal to k equal to 1, I have this transfer function. And the RLC circuit which we saw in our previous slides had a transfer function of this sort, which for r, l and c being equal to 1 again translates back to this one. Okay. So, these are same transfer functions for two different systems. Okay. But therefore, if I just say well 1 over s square plus s plus 1, it could mean more than one system. Physically, I could realize with as a mechanical system or even as an electrical system. However, what the transfer function does is say if my input is the voltage and output I know is the current, okay, let me write all in the Laplacian domain, then this Gs will have the appropriate units, right. So, it could be the impedance or the reverse of the impedance and so on, depends on how we look at the transfer. So, if I just write it in, so V of s would be the output I of s would be V of s over G of s. So, this should, so G of s here would capture the units of the inverse of the impedance. Similarly, over here also. So, the transfer function actually it captures the appropriate units to transfer the input signal to the output signal. If it is a force and a velocity, it will have an appropriate unit over here and so on. Okay. So, in general, a transfer function would look of this form, where y of s could be any polynomial of order m in S, u of s, the Laplace of the input, could be written as any polynomial of order n which comes in the denominator. I could also factor that as some number k prime, I will tell you shortly what this is, and into a series of what we call as zeros and what we call as poles. Okay. So, here I call n as the order of the system, m would be the number of zeros, n would be the number of poles. Okay. So, there is something called also the DC gain here, which is essentially what happens when I just supply a DC input. So, this DC gain is just obtained by substituting S with 0, and in this case it would just become Bm by An. Okay. If you are wondering where this comes from, it is just an application of the final value theorem to the output y of s equal to g of s u of s, right. So, when u of s is a step and I apply the final value theorem, s going to 0, s times g of s, what is this u of s? For a step input is 1 over s. So, these guys go away So, what I am left with is G of 0. Okay. So, this is we will refer to this as the DC gain of the system computed as Bm over An. Okay. So, these Z's are called the zeros of the system. I will shortly define them formally. P's are called the poles of the system, and if I write my system in this form, my DC gain again would be G of 0, that would be, okay, let us call this as k. So, the k here would be this number k prime over or multiplied by the product of all the zeros with a minus over, okay, so do a bracket here, over the product of all the poles. Okay. So, we will see shortly this k prime is important to us, right. Okay. So, one important thing to remember here is that the number of poles is always greater than or equal to the number of zeros, because if the system has more number of zeros, the system actually becomes non-causal if you have number of zeros more than the number of poles. For example, if I have a system s square plus 1 over s plus 1, right, this is a non-causal system, and this is also not physically realizable by any known components. So, and you could also look at it in a way that if I try to compute the inverse Laplace transform of this guy s square plus 1 over s plus 1, it will not exist. Similarly, if I just take even a simpler one s, right, and therefore, if in the future classes when we are designing a controller, its transfer function, if you analytically say, well, I got a beautiful controller which again has the structure like this, well, this is incorrect. This never be physically realizable. So, what we should be important in all through our problems is that the number of poles should always be greater than or equal to the number of zeros. If not, the system becomes non-causal and it will never be physically realizable. So, we will keep this in mind and recollect this again when we do a control design, and we will see how to actually overcome this problem, right. Okay. So, by definition, what are poles? Well, these are the roots of the denominator polynomial of the transfer function. Okay, how does this equation look like? So, just take this denominator polynomial and just equate this to 0, it will give me set of n solutions, and those are the poles of the system. And what happens to the system when s reaches the value of poles, when s is equal to some pi, Gs blows up to infinity, right. A very simple example could be something like this, right. I have s plus 1 over s plus 2, s plus 3, right. So, here the poles are minus 2 and minus 3, right. So, if s equal to minus 2, this value just goes to infinity. Okay. Similarly, zeros are the roots of the numerator polynomial. Set the numerator to be equal to 0, and what I then get are the zeros of the system. So, what happens when I evaluate the transfer function at zeros? This will always be 0, just substitute. So, in this case the zeros are at minus 1, and if I substitute minus 1 for s here, my value of transfer function becomes 0, because this goes to 0. Okay. So, these poles and zeros together with the system gain k characterize the entire input output response of the system. Okay. So, what do I need, or what have I learned so far is I can, given a transfer function, I can write my system as a set of poles, a set of zeros together with a possible system gain, right, and these three will tell me the exact behavior of a system given a certain input. Okay. So, let us see the system, right, given by 6s plus 12, s cube plus 3s square plus 7s plus 5, right, and I want to find what are this, what is the system gain, what are the poles and the zeros. Okay. So, the DC gain, just set s equal to 0 and I can easily compute this, the DC gain of the system is 12 over 5, right. Okay. What are the zeros? Set the numerator polynomial to 0, 6s plus 12 equal to 0, then this will give me S equal to minus 12 over 6 is minus 2, right. So, the 0 would be at minus 2. Okay. So, sorry, there is a little error here. So, if I compute, the zeros would turn out to be at minus 2. Similarly, I take the denominator polynomial, equate it to 0, and I get S equal to this 3 roots, right, S equal to minus 1 plus 2j and minus 1 minus 2j. Okay. So, what do we observe from here? That of course, the gain will always be a real number. The poles and zeros, they could either be real numbers like a minus 2 here, a minus 1 here, and if they are complex, they will always be in conjugate pairs, right. For example, there will never just exist a pole at minus 1 plus 2j. If minus 1 plus 2j exists, there will always be a minus 1 minus 2j, or in general the poles, complex poles will always be of this form, a plus minus jb, right. And this is because all the coefficients of my transfer function are always real values. Okay. The second thing is, well, if I have a system with different components, right, how do I visualize it? Is there a nicer way to represent that system, and how to understand the flow transformation of signals in a complex system, or given a series of interconnected systems, how do I find its overall transfer function, right? We will try to understand that phenomena a bit, right, and this is what we will usually call as the block diagram representation. Okay. So, what is a block diagram representation? By definition, it is just a shorthand pictorial representation of a system which depicts each of the system subcomponent, how signals flow within components or from one subcomponent to the other, and this block diagram will give me easier representation of these kind of systems, right. There could be multiple systems connected to each other and interacting with each other, and we will see also how having this kind of representation will give us some easier methods to find the overall transfer function of the system, given that I know transfer function of individual components or the individual subsystems. Okay. So, various simple building blocks for block diagrams will be of 4 components. One, I will have GS, which is the transfer function as we have defined so far. I will just have arrows to represent the direction in which the signals flow. Then I will have summing points. I have a signal U1, a signal U2, there is a plus and a minus here. The Ys would be computed as U1 minus U2s. If there is a plus here, it will simply be U1 plus U2s. Okay. Takeoff points, well, these are just like you are just adding an additional wire over here or something like that. So, if this is a U of s here, if I just put a wire here and take, the signal would still remain the same. So, this is a U of s here and the U of s also here, right. It just represents the branching of a signal. Okay. So, let us try to draw a block diagram of the simple circuit which we had started with, right. So, I have a V, I have a R and a C over here, right. The L we just omit for simplicity, right. So, I can just say that Vi is my U, O is my output signal, and just have a very simple block diagram representation of this is this form, right. So, you can just compute this transfer function to be 1 over 1 plus S times RC, right. This is very simple representation of the system. Okay. So, well, what happens if I have systems which are in this form, right. There is U of s which generates a certain Y of s via G1. This output serves as an input to G2. G2 will have a certain output which will serve as an input to G3 and so on. In this case, the transfer function is simply this one, Y of s over U of s is G1 times G2 times G3. Okay, let us see this. This is actually straightforward to compute. So, let me call this as Y1, let me call this as U2, let me call this as Y2 and U3 and so on. So, for G1, Y1s over U of s will give me G1 of s, right. Okay. Similarly, for G2, this will be the ratio of Y2 of s over U2 of s. Okay. So, Y1 is U2, Y2 is U3 and so on. Okay. So, Y2 of s is G2 of S times U2 of S. Okay. Now, what I know is this is G2 of S times Y1 of S. Okay. Now, what is this Y1 of S? Y1 of S is G1 of S times U of S. Okay. So, therefore, if I were to compute what is Y2 over U of S, that will simply be G1 times G2, right, again of S and S here. Similarly, I could even do the third cascade. So, I will get the overall Y divided by the overall U would just be G1 times G2 times G3. Okay. So, this is what I call as the series connection, series interconnection, in which case the transfer functions just multiply. Okay. Similarly, I can also have components interconnected in parallel, right, and then okay, what would be the overall Y of S over U of S. So, let us say that this U1 via G1 generates an output of Y1 of S, here I have Y2 of S and here Y3 of S, and by the definition of the summing block, Y of S would be Y1 of S plus Y2 of S plus Y3 of S. Okay. What is Y1? Y1 comes via G1 and U1. So, I will have G1 of S times U of S plus G2 of S times U of S plus G3 of S times U of S, and resulting in this expression that the entire G of S is Y over U is just a summation of these three, G1 plus G2 plus G3. Okay. I could also have things connected in what I call as a negative feedback loop, right. So, I have a signal here, it goes via G, it is, and this Y is fed back via H of S again over here, right. So, how does the transfer function look in this case, right. So, in the feedback form, okay. So, I want to find out what is Y of S over U of S. Okay. So, let us start from here. Where does this Y of S come from? Y comes via G and E, written as Y is G of S times E of S. Okay, this is nice. Okay, where does E of S come from? E comes as U minus Y of S times H of S, right. There is a little summing block here with a plus and a minus. So, E is plus of this signal minus of this signal, right. So, this I write here U of S minus Y of S H of S. Okay. And I just do a little simplification. So, I just say Y of S is G times U minus G H and Y. I eliminate, or I just get this guy to this side, and I just get that Y of S by U of S is G over 1 plus G times H, right. And this is as we call as the negative feedback loop, and we will use this very extensively throughout this course. So, it might help you just to memorize this thing as a formula, right, that if I have a G here, a H here, Y over U, or the overall transfer function, this I could even call as the overall transfer function. Between Y and U, given these individual transfer functions here, right, the forward transfer function block has G of S, the feedback one has H of S, and this is the overall transfer function from Y to U as G of S over 1 plus G times H. Okay. Now, is this always true? If I say that I have G1, I have a G2, that the overall thing is always G1 times G2. Right. When I do this, I just everything is in S. So, I just sometimes omit this, but just assume that this is all in the Laplacian domain. Is this always true? Right. So, let us first talk of with an example, right. It is in this slide, right. So, I could possibly if I just be a little lazy, I could just look at this system as I have this one RC circuit connected to another RC circuit. Okay, how did the transfer function of this RC circuit look like? Okay, let us go back few slides. So, this looked like something like this, 1 over 1 plus S times RC. Okay. So, the transfer function of the first guy would be 1 over 1 plus S R C. The second guy would be the same, 1 over 1 plus S R C. Now, the question to be asked is this the overall transfer function? Okay. Okay, let us see if that is the answer. Okay, let me just derive this transfer function starting from the 4 steps which I had listed out earlier, right. I just write down the individual equations with the KVL here, a KVL here, and then just compute V output by V input. Okay. The first loop says Vi of S is Ri plus 1 over Sc I1 minus I2. Similarly, I could write down the expression for VO, and VO explicitly written down is in this form. Okay. Now, I do all the math, and the transfer function obtained by just eliminating I1 and I2 would be simply like this. And this guy is not equal to the product of the individual transfer functions, right. The overall transfer function of this system is not equal to the product of the transfer function of the 2 individual RLC circuits, even though they seem as if in cascade. Okay, what is going wrong here? Okay, so there is a catch here, is that whenever I want to do an interconnection like this, right, the assumption is that while deriving the transfer function, there is no loading, right, that there is no power drawn at the output of the system, right. So, this assumption must be satisfied all the time while deriving transfer function in this form, right. So, if one component is acting as a load on the other component, the transfer function can, it just cannot be determined individually, right. So, we should actually look at both components together, right, they should look at in combination, right. Okay. So, what is happening here? If you see this circuit, the overall transfer function is not equal to the product of the individual transfer functions, right. This is because again the assumption of no loading fails. Okay, how does it fail? The second RC circuit, it draws energy from this component here, right? This one, right. It draws energy from, so this is where my output is measured for the first guy, right, from here till here, right. So, this circuit draws energy from the first one, and hence its individual transfer function is not valid when it is in cascade. So, this is what we have to be careful when we apply the formula of 2 transfer functions in cascade, the overall transfer function being the product of it, right. Okay, we will possibly see a little more examples on this, right. For the moment, we will just conclude by saying that this is not always true, right. Of course, then there are ways to make this which we will postpone to a little later. But before that, let us try to do what I would call as a block diagram representation of a transfer function, right. A very simple example, I take DC motor, which is also called a separately excited DC motor. The field is supplied by an external source. I have the armature, certain armature resistance, a certain armature inductance, and this we know produces a back EMF. This back EMF results in a torque which produces a certain displacement theta, right. If I consider J and D to be the moment of inertia and the frictional component of the motor. Okay. So, in this subsystems, what are my components, right. So, if I call, okay, so if I denote Ra as the armature resistance, armature inductance, the current of the armature. Okay. So, if I just write down the equations for this, right, the first one. So, I have EA as the applied voltage, okay, this is RA, this is LA, right, and this will have a certain back EMF, right. So, the first of my equations, if I were to write down, would be EA equal to, if I just call this IA from these notations here, this is IA, RA, okay, I write everything in the Laplacian domain, R A plus S L A plus E B, okay, or E A minus E B is I A R A plus S L A. Okay. So, what happens next? Once this back EMF is generated, I will have a certain torque resulting in a displacement theta, and of course, taking care of the moment of inertia of the motor or possibly even the load, and D would be the combined frictional component of the motor and the load. Okay. So, there are two things here. One is the back EMF constant and the other one is the motor torque constant. Okay. So, let us first look at how this block diagram is generated, right. The first thing, in the previous slide I had this thing, right, that E A minus E B is the armature current R A plus S times L A. Okay. So, if I were to write this as a block, right. So, the first block would say that E A generates a certain armature current here, right. So, as this E A as the input possibly, or which results in a certain armature current, right. Okay. So, how will that look like? So, we will slowly try to achieve this bigger block diagram here. So, I start by saying E A, right, there is a negative sign here. So, E A minus E B, okay. So, E A minus E B, if I would write this in a better way, E A minus E B divided by R A plus S times L A gives me I A, right. So, E A minus E B goes via a block 1 over R A plus S times L A to give me I A. Okay. Everything is again in the Laplacian domain, right, in this direction. Okay. So, what do we know, right, in a motor, that the torque is proportional to the field current and the armature current, right. The basics of a DC motor teaches this way. But here my field is constant, right, it is a separately excited machine. So, if you go see this picture here, this is always constant, EF is constant. So, the torque as a result of this would have a constant effect. Therefore, what is variable here is just the armature current. As the load varies, the armature current would vary, and therefore, the torque I can rewrite as T is some torque constant times the armature current. Okay. So, I will have K T and the T M here. Okay. Okay. Now, what does this torque do? Well, this torque, so we had seen this relation for rotational motion, right, between torque and the angular velocity, right. And what does it go through? This torque goes through the J, the moment of inertia of the motor and the load, and the friction, right. So, the torque is related to this thing, right. So, T M goes via this thing via J S square plus, okay. So, the relation between the torque and the angular velocity is given, it goes through this, it generates a theta dot, okay. And this theta dot, I can integrate this, an integral component would look like 1 over S and I get a theta S. Okay. Now, how to close this loop, right. So, I have that the back EMF is proportional to the speed of the motor, right. So, here we define Kb as the back EMF constant. So, if you recollect the basics of DC motors, I will have Kb times theta dot, okay. So, this theta dot of S via Kb completes my entire loop here, right. So, again let us go through the process, right. So, with an arrows in this direction. So, my voltage, input voltage first generates an armature current.
What point is theta dot of S? It should be S theta of S.
Yeah, I was about to say that. Okay, so there is a question of what is this theta dot of s. We said we will eliminate differential equations, but then there is a theta dot of s. So just an abuse of notation, theta dot of s actually means s theta s, right. So I am just using the notation here a little bit, but this actually means this one, right. So that will keep that in mind. So I just wrote this just to make it a little obvious that we are dealing with the angular velocity, right, and we are used to this differentiation. So theta dot of s essentially would mean s times theta of s, right. Okay. So again back to this. So we start with input voltage which generates a certain armature current, okay, and this armature current results in a torque results in a certain angular velocity, and this angular velocity I can integrate to get the displacement. And I also know that to close the loop, that Eb is related to theta dot via this expression, right, and then I have this entire closed loop system, right. So I can rewrite, okay, how do I get the transfer function for this, right. So let's for simplicity say I just ignore L for the moment. So I will have EA, a negative feedback loop, and so I'll have a single block here, right. So all this would simply be multiplied. So I have 1 over RA, I have KT, I have 1 over JS plus D, I have a theta dot of S, then a 1 over S, I have a KB here, this guy goes from here till here, and this, right. So now how do I write the overall transfer function as the ratio of the output displacement to ES, okay. So I'll just recall what properties I learnt about the block diagram earlier, right. So here I have G of S, H of S is G plus 1 over G times H, okay. So I go back to my block here, okay. So let me call this G of S, I call this H of S. So my overall block here would look like G of S over 1 plus G of S H of S, okay, and then this would be multiplied by 1 over S, and I can just write down the final expression that this will look like straightforward computation which can be done very easily. KT over RA over JS square plus S D plus KT times KB, entire thing multiplied by RA, right. This is, you can just do this calculations from here to here, right. Okay. So what have we done so far? Well, we had defined transfer functions and its properties. We had seen how defining a transfer function helps in block diagram representation of complex systems, and also saw some special cases where two systems in cascade do not their Laplace transforms do not directly multiply, or the transfer functions do not directly multiply in case there is loading effect on the transfer functions, okay. So what we will next look at is, if I have a system which has lots of summing points, lots of negative feedbacks, how do I simplify those block diagram of a complex system and then to find the overall transfer function. We will also then see how we can actually use this transfer function to see how my systems would behave to different kinds of inputs. Okay, thank you.